Hey everybody out there in YouTube land. Yesterday or last lesson I promised you that we would be focusing more and more on particle motion, or the application of calculus to basic physics and to basic real world concepts. So last time we talked about the relationship between the position of a particle and the velocity of the particle. And we didn't really, we did mention the idea of this relationship between velocity and speed. Well, today we're going to focus more on that relationship so we understand the difference between them and how to approach different problems depending on what it's asking for, and being able to interpret the question so that we understand whether it's asking for speed or velocity. So with that said, obviously, the objective is to be able to explain the difference between the velocity and speed, and most of you probably already know that the speed is the absolute value of velocity, but how does that play out in calculus, I guess, is the really important thing, okay? So, first of all, the definition of velocity is the rate and the direction an object is moving. So, like I have previously said, velocity is how fast something's moving, but it's also telling us which direction it's going. Now, within our scope, within our world, we're going to really just focus on one direction or the other. We're not going to be living in the realm of three-dimensional movement. We're going to be moving forward and back, or left and right, or up and down. Now, we can combine all those and do calculus on all of that, with vectors and things like that, but we're really going to just focus on along basically an x-axis, if you would. So when we say that the velocity is negative on the x-axis, that would imply that the particle is moving to the left, and if the velocity is positive, the particle is moving to the right. Okay, so we talked about last time that velocity is the derivative of the position function. We could also say it's the derivative of the displacement function. Either way, it's going to work out the same way. And again, we'll talk more about that idea of position and displacement at a later time, okay? But this is some very important stuff. Because velocity is the derivative of position, we know that if the velocity is positive, that would imply that the position graph is increasing, okay? So another way of looking at that a little bit is if my velocity is positive on a number line, so here's my number line. If my velocity is positive, that means the particle is moving to the right if velocity is positive, okay? And if velocity obviously is negative, that means we are moving to the left, okay? But the correlation here is something that's very important. If I were to graph the position time graph of this relationship, okay? If I were to tell you that the velocity is positive, then that would mean the position is increasing because we are moving to the right. So if the velocity is positive, we are going to see the position going up. Now, when the velocity is negative, you're going to see the position going down, okay? Now, when we cross the t-axis in regards to position, that implies that we are on the left-hand side of zero. So if this graph is moving up, that means we're moving this way. If the graph is moving down, we're moving that way. If the graph is positive, that means we're on the right-hand side of zero, and if the graph over here is negative, then we're on the left-hand side of zero. But the really important relationship is that if we see velocity is positive, that implies that the position is increasing. And you can see that because remember, velocity is the slope of the position function. So the slope is positive in this region, so therefore velocity will be positive, okay? Increasing function implies positive derivative. That's important. Increasing function implies positive derivative. And then conversely, positive derivative implies increasing function, okay? So when the derivative of the position is greater than zero, okay, that's fine. So we'd say it like this. We'd say that the velocity is equal to the derivative of the position graph, and therefore it would be greater than 0 there. Okay, and in the opposite manner, if velocity is negative, then the position is decreasing, which would imply that the derivative of the position, or the velocity, is less than 0 being negative. And we say velocity is the derivative of position, which in this case would be less than 0. The last thing is this, and this one's important. If velocity is 0, that implies that the particle is at rest. That means the position is not moving. If velocity is 0, there is no change in the position, okay? When the position doesn't change. Or in other words, when the derivative of the position function is 0. So we say velocity, which is equal to the derivative of position, is 0. So there's a lot of verbiage, a lot of language here. It's good to read it and really understand those relationships. And I'll let you pause the video and look those things over. All right, next thing, next terminology, speed. Speed is the rate that an object is moving. Well, didn't you just say that velocity is the rate at which an object is moving? Yes, but velocity had one extra thing to it. Velocity said that it's how fast it's moving, the rate, but it also implies direction, where speed doesn't imply direction. Okay, direction is irrelevant when we talk about speed. Okay, if x of t represents displacement or position, okay, if x of t represents displacement or position, let me write this down, x of t is position, okay, then we know that, x prime, x prime of t is equal to v of t, which is the velocity, okay, that's fine. Okay, then how do we express speed? Well, speed, we don't really have a function name for it. Speed, in respect to time, is equal to the absolute value of velocity. They're the same thing, it's just that speed is absent of a sign. And then we could say, if that's the case, then it's also the absolute value of the derivative of position. Okay, so think about that for a second. Back in Math 1, Algebra 1 ideas, we really focused on the idea of a function, and whether it's above or below, really we focused on a linear function. So if I had a velocity that looked something like this, then what does the speed graph look like? The speed graph is going to be the reflection of the velocity graph. So if this is v of t, then the speed graph, well, whenever the velocity is positive, the speed will be the same thing, right? It'll be the same thing. But whenever velocity is negative, the speed will be the opposite of it because it's the absolute value of it. The point is this. If velocity were a linear function, just an example, if it were linear, then the speed function would be an absolute value function, okay? So speed is the absolute value of velocity. All right, so let's take a look at an example of this. This one's pretty basic, okay? We have a function, x of t. So this is my position function, is equal to 3 sine of t. All right, and it represents the displacement or the position. Right now, we can kind of interchange them. Later on, we'll define those a little bit clearer. The question is, what is the velocity and the speed when t equals 3 pi over 4? What is the velocity? What is the velocity and speed at t equals 3 pi over 4? So how do we find velocity? Well, velocity is equal to the derivative of position. So we need to figure out our derivative. This is pretty straightforward. Well, notice the rules here. We've talked about the product rule. We've talked about the constant multiple rule and all these things. I'm going to do this a couple different ways. If I treat this as a constant multiple, and it is, remember, in order to take the derivative, we take that constant multiple, ignore it, find the derivative of the function. The derivative of sine of t is cosine of t. and then multiply it by that constant. So that's the derivative. If you wanted to view this as the product rule, because remember I said anytime you see a multiplication sign, it should be at least going through your head that you could use the product rule. It doesn't mean you always have to use it because this was easy. But we fall into the mistake of not using the product rule when we should. So if I were to use the product rule, remember the product rule says the derivative of the first thing, so the derivative of 3 is 0 because it's a constant, times the second thing, plus the derivative of the second thing, which is cosine of t, times the first thing, so times 3. And so you can see that this is the same as that. So velocity function is 3 cosine of t. Now, I want to know the velocity at 3 pi over 4. So velocity at 3 pi over 4 is equal to 3 times cosine of 3 pi over 4. Okay? And we just got to calculate that. Well, cosine of 3 pi over 4, 3 pi over 4 is there. Cosine is going to be negative rad 2 over 2. And so our velocity at 3 pi over 4 is negative 3 rad 2 over 2. And the units on this guy were, what were they? They were seconds and feet. So this is going to be feet per second. So that's my velocity. Okay, so what's that tell me? That tells me I'm going at some rate. I don't want to calculate the decimal values there, but it also tells me that I'm moving to the left or I'm moving backwards. Okay, now let's calculate speed. Speed at 3 pi over 4 is equal to the absolute value of v of 3 pi over 4 because speed is the absolute value of velocity. Well, that's pretty straightforward. It would then be the absolute value of negative 3 rad 2 over 2. And so it would be 3 rad 2 over 2 feet per second. So this is our speed when t equals 3 pi over 4 there. Okay, so that is an example of comparing the two. That's pretty straightforward, I think. Just make sure I got these answers right. Negative 3 rad 2 over 2 and, whoops, and 3 rad 2 over 2. Okay, so that's good. Let's go ahead and look at the next thing. We've got a practice problem here. So if you want, you can go ahead and pause it and see what you come up with this problem. And then push play when you're ready to go on. Here we have S of t, and S of t represents the distance you are from home. In other words, it's your position. So S of t is the position, and it gives us a polynomial expression, t cubed minus 21 over 2 t squared plus 30t. Okay, and it gives us a interval or a domain from 0 to 7. All right, and then we just answer the three questions. When is the particle or when is the object stopped? When are you stopped? When are you not moving? When are you moving in the positive direction and when are you moving in the negative direction? Well, if I was to approach this graphically, now I don't know exactly what that looks like. I guess I can factor a little bit to figure out roughly what it's going to look like. I know that I have a 0 at t equals 0 because that factor there. And I don't know that exact graph. I already have it put up here. I can spend some time doing that, but I'm going to go ahead and just look at it on the lesson here so that we can see it a little bit better. So this is the graph, or a very rough graph, of the position function. And we can verify that because that's t cubed. So this is a cube function. And it says, when are we stopped? Well, if this is the position graph, think about when we're stopped. We're stopped when we're not moving. When are we not moving? We're not moving when our velocity is 0. How do I find the velocity? Remember, the velocity is the derivative of position. So I am asking for when the derivative of this graph is 0. In other words, when is the slope of the tangent line 0? And we can see that the slope of the tangent line being 0 at this point here and this one here. So that's going to be when t equals 2 hours and t equals 5 hours because we have horizontal tangent lines. That's when we are stopped. Now, some people might argue, well, you're not actually stopped because you turn around and went the other way. But we did stop for basically a split second, or not even a second, but an instantaneous point in time, we stopped. Okay? For B, it says, when are we moving in the positive direction? So when are we moving to the right, or when are we moving north, or whatever positive is defined to be? When are we moving in the positive direction? We're moving in the positive direction when the velocity is positive. Okay? Well, when is the velocity positive? The velocity is positive when the slope of this graph is positive, or in other words, when this graph is increasing. So this graph is increasing from 0 to 2 and from 5 to 7. So we'd write it from 0 to 2 and from 5 to 7 hours, essentially. And then for C, when are you moving in the negative direction? We're moving in the negative direction when the velocity is negative, which implies that our position graph is decreasing. Okay? So we can see that that's taking place from t equals 2 to t equals 5 hours. So that's the graphical approach to this problem. What I want to do is approach this analytically. I want to answer the same 3 questions, but I want to do it analytically because I'm going to introduce something new for you today that we're going to apply into the future as one of the most important principles of calculus and one of the most important things in terms of passing the AP exam. Okay, this is the introduction for it today. So how do I know when the particle is at rest? I'm going to take a little note of this. We are at rest when v of t equals 0. When are we moving to the left? We're moving to the left when v of t is negative. When are we moving to the right? We're moving to the right when v of t is positive. So the bottom line is it all depends on the velocity. So what I need to do is figure out the velocity. So what's the velocity? The velocity is the derivative of position. So let's go ahead and figure that out. The velocity is the derivative of this guy. This is polynomial. It's pretty easy. It's just all power rule. The derivative of t cubed is 3t squared. The derivative of negative 21 over 2t squared is going to be negative 21t. And then the derivative of 30t is just 30. So there's my velocity function. First question, when is the particle at rest? The particle is at rest when v of t equals 0. So we're going to say at rest. This is my work for at rest. We'll set velocity equal to 0. So 0 equals 3t squared minus 21t plus 30. And whatever solution we get here is our answer. So notice we can factor out of 3, and we're left with a quadratic. That's convenient. Oops, factor out of 3, we get 7t plus 10. And then that still factors. If it doesn't factor, it would probably be a calculator problem ultimately. And so we end up with that factor, and we can then say t equals 2 and 5. So same answers as we see in our graph. The particle is at rest when velocity is equal to 0. Velocity is equal to 0 at t equals 2 and 5. So therefore, when t equals 2 hours and 5 hours, that's when we're at rest. Okay? That's our answer for at rest. The next question, it says, when are we moving in the positive direction? Now, you may have an idea for how you would figure out when this graph is positive. And I'm not going to criticize your idea. But what I want to do, what I want to do is show you a nice, clean way of seeing when velocity is positive and negative. So one thing I want to recognize is that if I set up a number line, for my velocity graph, okay, just a number line, not XY graph, but a number line, I would recognize that when when time is 2 and when time is 5, okay, we know that the velocity is 0. When t equals 2 and t equals 5, the velocity is 0. We did all that math there. Now, the question is, in this case, and we're going to get more in depth with this as time goes on, is there any other zeros? And the answer is no. We only have 2 zeros here. Okay? So that would imply that for every value to the left of 2, the sign has to be the same. And here's why. Because if it was negative, if velocity was negative in this interval, and then it was positive somewhere else within that same interval, that meant that velocity changed signs somewhere in that interval. Well, we know that it didn't change signs somewhere in that interval because it can only change signs when the velocity is 0. And we already have all our zeros. So that means the only place where velocity can change signs is when t equals 2 and when t equals 5. So as a result of that, we know whatever sign is here at any point in this domain will be the same sign throughout the entire domain. Same thing here and same thing here. And so what I do is I do a little experimentation. I pick a time to the left of 2. So let's say when t equals 1. So I'm going to figure out what v of 1 is. Well, v of 1 is 3 times 1 squared minus 21 times 1 plus 30. Well, that's equal to 3 minus 21 plus 30, which equals to, let's see, that's 9 plus 3 is 12. I don't really care what the value is. What I care about is the sign. What I notice is that when t equals 1, the velocity is positive. Now, you can pick any number to the left of 2, and you'll get the same answer. Not the same numeric answer, but you're going to get the same sign. So I've got this work to show here. Let's go ahead and check the interval between 2 and 5. So I'm going to pick a time between 2 and 5. So let's figure out what the velocity is when t equals, let's say, 3. Well, v of 3 would be 3 times 3 squared minus 21 times 3 plus 30. And then we simplify that. That's going to be 27 minus 63 plus 30. 27 and 30 is 57 minus 6 is negative 6. And so we can see that the velocity when t equals 3 is negative. That implies that the velocity will be negative throughout that entire interval. Okay? And then we'll do the same thing for a time that is greater than 5. So I think the easiest one is probably going to be 5 itself, or sorry, 6. Let's use 6, because that's the right of 5. So we got 3 times 6 squared plus 21 times 6 plus 30. So that's going to be 36 times 3, so it's 90, that's 108, minus 126 plus 30. So let's see, that's 138, so that's going to be a positive 8. But the important thing, again, is the sign. So we know that the velocity for every value to the right of 5 is positive. Now, I know some of you are probably looking at this going, you wasted all that time. If that's positive, then that's got to be negative and positive because it has to alternate. That is not true. It does not have to alternate. It could have been positive, positive, positive. It could have been positive, positive, negative. You have to check at least one value within each subinterval to see what's going on. Okay? So now that we have this number line that represents the signs of velocity over all these different intervals, I can answer the question in part B pretty easily. And the question in part B said, when are we moving in the positive direction? So we would say moving in the positive direction, whatever that implies, direction, over 0 less than t less than 2, and 5 less than t less than 7, and that would be hours was the units. Now we always need a justification, and this is the important part. Years ago, the AP exam allowed number lines to represent our justification. Number lines are no longer allowed in and of themselves, so we have to use a verbiage that explains what we're looking for in the number line. Okay? So we would say moving in the positive direction over those intervals since v of t is positive. Okay? So we are moving in the positive direction, or our position is increasing since velocity is positive. Now we can answer part C based on that, based on the same amount of work that we did here without adding anything to it. When are we moving in the negative direction? We're moving in the negative direction. Running out of room here. Negative direction. over 2 is less than t is less than 5 hours. And the justification is since v of t is negative. Okay? So this is going to be a huge connection, a huge application of calculus as we move forward. And it's not just particle motion, but particle motion gives us an idea of what's taking place, or gives us a context that we can apply calculus to so that we can have a good understanding of it before we jump into more applications. But the bottom line is, how do we know when we're at rest? We know we're at rest when velocity is equal to 0. Remember, velocity is equal to the derivative, so we took the derivative and set that derivative equal to 0 and solved when it's at rest. Then we determined the signs of velocity over the intervals between the endpoints and the zeros, essentially. And then we can see when the velocity is positive, the particle is moving in the positive direction, or the function is increasing. And then when the velocity is negative, we know that the position is decreasing. Okay? So with that said, let's go ahead and summarize that. I kind of have it all here, make sure I've got it right. And I use different values in this case, and that's okay. But we can see our answers are consistent with what I have up here, so that's perfect. All right, the next thing we're going to talk about, and again, I want to emphasize this. This is so important. This concept here, the idea of the number line, is so important, okay? The next thing we're going to talk about is how to graph a speed function, okay? How to graph a speed function. Now, we already have the graph of the position function. We had that earlier on, okay? And in fact, we kind of can see the graph of the velocity function based on what we just did in our work a second ago. So let me go back to that velocity graph, sorry, that position graph that I had. We know that this graph goes up and then down and then up again. So when t equals 7 and t equals 0, and then this was t equals, I believe, 2 and t equals 5. Those were the key components to that. And so let's go ahead and jump ahead here. How do we graph the velocity and the speed? Well, if this is my position graph, remember velocity is the derivative. So if I want the derivative of this, let me go ahead and put it right here. We're going to identify the same key points. Now in the graph, or sorry, in the number line that we just created, that actually provides for us what we need, because it gives us the signs of velocity. Well, we knew that the velocity was 0 when t equals 2 and when t equals 5, right? And we knew that the velocity was positive over this interval 0 to 2. So we're going to have something here. And then it was positive also in 5 to 7, so we're going to have something above there. And then it was negative from 2 to 5. Okay? So we're going to have something that looks kind of like that. Now remember, the next step in graphing a derivative function is to determine the steepest points. And so here, for the interval from 0 to 2, the steepest point is actually at the beginning there, at the end point. And so we would say, since it's steepest there, this will either be the highest point or the lowest point. It's going to be the highest point because it's positive. So we'll just put like a high point here. We don't know exactly what it is. We're kind of estimating. Where's it steepest in the interval of 2 to 5? Well, it's steepest at this point here. So maybe it may not be exactly in the middle, but we can kind of guesstimate that there to be there. So we'll put a point there. And then where's it steepest from 5 to 7? Well, we see that it's steepest maybe at the end here. And again, it doesn't necessarily have to be at the end, but in this case it is. So it'll be the highest point on this side. And then from there, we just make sure that we kind of connect those dots in a smooth manner. Okay? So this is our velocity graph. Obviously not drawn to scale, not drawn perfectly. Let's say that's 2 and that's 5. But the thing that I want to emphasize here, and I think it's important to see, okay, the graph, or the function that I originally was dealing with, the position function, is a cube function. Right? We see the cube here. Well, what do we see in the derivative of it, the velocity? We should see a parabola, because when we take the derivative of this, the highest exponent would be a 2. And we generally see a parabola. So it's a good way of understanding how these derivative graphs work. Now, the next question that we have to ask, or the next thing we have to do, is figure out the speed of speed graph. Okay, so this is my speed graph in respect to time. What's different about the velocity graph and the speed graph? Well, remember, speed is the absolute value of velocity. So that means whenever velocity is positive, the speed is the same thing. So we're going to get the same exact look from 0 to 2, and the same exact look from 5 to 7, something like this. Okay? But when velocity is negative, what is the speed? The speed is the same numeric value, but it has no sign, or it's positive. So we would take this and actually reflect it over the x-axis, and so we end up with something like this. So this is the graph of the speed function. So position, velocity is the derivative of position. So since that's cube, this will be a parabola. And the speed is the absolute value of velocity. So anywhere that this is negative, the velocity is negative, this will be positive. So it just reflects up. Okay? So that's how you graph a velocity and speed function. And so if you want to see, I guess, it a little bit, maybe a little bit clearer, you can see it here. There's my velocity, and there is my speed bouncing up, reflecting over the x-axis. All right. And our last problem for today is our exit problem, dealing with projectile motion. And actually, this problem is actually related to Math 2 stuff. Most of you will probably try and approach this through a Math 2 mindset. And that's okay at first, but I want you to think calculus, because we're gonna change things up, and we're going to use way more difficult functions than the one that I'm giving here. In this case, it says a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of, given by s of t we'll say, equals 160 t minus 16t squared, okay? How high did the rock get? So a dynamite blast it blows up, and this rock goes up into the air, and then it comes back down. Well, it follows a parabolic path. So if you were in Math 2, or if you were in Algebra 2 or Algebra 1, depending on where you learned it, you would see a parabola that looks something like this, right? On the time graph, the height or the position time graph. And if I said, what is the maximum height, or how high did the rock get, that would be the maximum. That would be, well, I just got to find the vertex. And so we'd do the negative b over 2a, and then we'd plug that value into t to figure out the height. That would be the Math 2 or the algebra approach to it. But I want to approach it, through a calculus sense. I guess we can look at this graph to understand it. When in this graph is the object the highest? Well, that's here. What do we recognize in terms of calculus about that point? That point, if we were thinking calculus, is the point at which the tangent line is a horizontal tangent line, okay? If that's the case, if we have a horizontal tangent line, that implies that the derivative is going to be equal to 0, right? Remember, we want to know the velocity of this object. This is the position of the object. If I find the velocity of this guy, let me write it over here, velocity of this guy is going to be 160 minus 32t. That's my velocity function. Now think about it. At the highest point, that means we were going up, and now we're going down. What is the velocity at the highest point? The velocity at the highest point must be 0, because for that split second, that moment in time, it was not going up or going down. So we set the velocity equal to 0, and then we solve that equation. So we end up with 32t equals 160, and then we go ahead and divide that. 160 over 32, let's see, that's 80 over 16. Divided by 8 is 10 over 2, which is, it looks like it's 5. So when t equals 5, the object is at its highest point. Now the question was, how high did the rock go? So we're going to have to take that and plug it in there. So we'd end up with not v of 5. We don't want to plug it into the velocity function. If I plug 5 into the velocity function, I would just get 0 out, because that's how I got 5 to start with, is when velocity was 0. I want to know how high it is, And how high it is given by the position function. So s of 5 is equal to 160 times 5 minus 16 times 5 squared. So let's see here. 160 times 5 is 500. That's going to be, let's see, 500 and 300. That should be 800. And then 25 times 16, doing math off to the side, back in elementary school here, 15, 0, 5, 2, that's going to be 400, so minus 400. Okay, and so our position, or our height, when t equals 5 is 400. So the maximum height, max height, is 400. 400 what? 400 feet. 400 feet. So that is our maximum height. Okay? Thinking through that, through calculus, the maximum height must occur when the velocity is equal to 0, because that implies that we're neither going up or going down. We can make this function a lot more complex. If this was the function where it was going up and then down and then up and then down, right? Let's maybe say it's some sort of multiple stage rocket where one engine fires it up, and then once it gets to the top, it stops, and so it starts falling, and then at another point in time, another engine fires up, and then it goes higher again. If I wanted to find the maximum height of this guy, I would approach it the same way. I would take the velocity, and then I would set the velocity equal to 0. In this case, I would end up with 3 places where the velocity is equal to 0. And then from there, I'd have to find the position of all 3 of those points and then compare which one produced the highest value. Now, I'm kind of getting ahead of myself. We're going to do a lot of that kind of comparison and analysis later on, but it's just an introduction of where you might see this, okay? So with that said, I guess I should make sure that I did this right. Looks good to me. That's perfect. With that said, that wraps up this lesson in comparing velocity and speed and position, and then a little bit of application of that. The big thing from today's lesson is figuring out that number line. If you can determine when the velocity is 0 or when the derivative is 0, and then you can determine the signs of the derivative or the velocity function in those intervals, that's going to go a long way in answering a lot of questions in the future. So if you have any questions for me, please comment below. And otherwise, I will talk to you later.